Hi everyone, today I'm going to make notes on transforming the parent function of the absolute value function, which we see here. So if the parent function of the absolute value is f of x equals the absolute value of x, and we see it's centered at 0, 0, this is its vertex. Its min, its origin, 0, 0. And then it just goes up 1 over 1, up 1 over 1. It has a slope of 1, and it happens to go on the same slope in both directions, positive and negative, of y equals x and y equals negative x. And all the transformations we're going to talk today are going to take this parent function, its graph, and move it left, right, up, down, make it look taller or vertically stretched, or make it look flatter or vertically compressed with both the arms of the absolute value function getting compressed down. And we're going to look at all the things in its function, so its equation that could make it do these things, its parameters. So the full amount of functions that could happen, if I take f of x equals the absolute value of x, I could multiply any amount of constants, so constants a, b, c, and d, and by constants I mean they're just numbers. Literally any numbers could fill these places. We could multiply an a out front of the absolute value, multiply a b on the inside of the absolute value, add or subtract some value c on the inside, and add or subtract some value d on the outside. On my test, we're not actually going to be going over any b transformations, so there will be no horizontal stretches or compresses. So I simplified it down to A, C, and D. And actually, when we only look at these transformations that happen, sometimes you might see formulas where it's x minus h plus k. But for the sake of my own personal students and not confusing you with any extra letters, I'm just going to stick with A, C, and D. And know that we're not going to be doing any B transformations in this video. If you want to learn those are specifically for SAT questions or higher level mathematics. If you want to get prepped for the SAT, please ask me how to do those on your free time. But let's look at a couple of these transformations in its entirety just to generalize what they can do. So, in short, the a value, the number multiplied in front of the absolute value, could be considered entirely its slope. It'll tell you how much do I rise, how much do I run at any one time. So it would make sense to say if our a value is greater than 1, so 2, 4, 3,000, 5/3, anything that's greater than 1. It could be 8.77, whatever it is. You could consider its slope and think it's going to make the graph grow faster, so it's going to look taller. An example of this would be a vertical stretch. So imagine I take the arms of an absolute value function, and then I'm simply going to, let's see, make it taller and taller and taller so it looks that's a bad example. Something that looks like our absolute value function, it's going to just look taller. It's going to grow faster and faster and faster than it normally would. Whereas if a is less than 1, specifically less than 1 and greater than 0. So the greater than 0 part talks that it is not negative. A being negative is completely its own transformation. But let's say a is some number that's a fraction or a decimal, like 0.5 or 3/4, anything that's less than 1. If I multiply that out front, this is going to compress the arms down. And if that makes sense, if my slope is 3/4, then that would be up 1, 2, 3 over 1, 2, 3, 4. That looks a lot flatter than, let's say, a slope of up 1 over 1, up 1 over 1, up 1 over 1. That seems to be growing ever so slightly faster. So having a fractional slope obviously makes it look flatter, so we say it's a vertical compression. So as I said, if a becomes negative, any negative number. It could be, so let's say a vertical stretch happens or a vertical compression happens. Instead of it going taller or instead of it going flatter, if I make it negative, it would just be doing the flatter or the stretched transformation in the negative direction. So if a is negative, we call flipping across the x-axis a reflection. Now the graph is all opening down. So a reflection across the x-axis. Whereas we have C and D a little bit more straightforward than A in that D the easiest transformation, I would say, out of the equation just moves the graph up and down. And it means exactly what it says. If I add some value d, I'm moving up. If I'm subtracting some value d, I'm moving down. Whereas if I have a value c on the inside, and notice it says minus c, and it does that on purpose. And that is to give it this idea that the insides are always the opposite of what you would think it would do. So let's say I give you a c value that is positive. Then that would be the absolute value of x minus a positive number, like let's say 2. Because c was positive and I plugged it into this formula of x minus a positive number 2, I'm really moving positive right 2. Whereas if I plug in a negative number, like c is less than 0, then that would be x minus a negative number, like negative 3. And we know that minus a negative is the same as x plus 3. But initially we plugged in a negative value. I'm moving left 3 in this case. So let's practice these. Let's say I'm given the value y equals the absolute value of x plus 3. Then I would just be moving up 3. This is the value d on the outside. And like I said, it's exactly what it looks like. Adding is up. Subtracting, minus 2 on the outside, is down 2. Now what would these look like? You would simply take the entire graph and shift it up 3 units or down 2 units. So let's say I wanted to do the down 2. I would take the vertex is probably the easiest point to shift down because we're starting at 0, 0. And if I move it down 2 units, I am now at 0, negative 2. And then I don't even have to worry about moving the other points down. I could. But instead, if I know the slope, which is still 1, it's the a value multiplied in front, then up 1 over 1, up 1 over 1 stays the same. So I have a vertex at negative 2, and I go up 1 over 1 from there, up 1 over 1 there, and we have a nice easy sketch of a graph that has not changed its slope, has not stretched or compressed, has just simply moved down 2 units. So an example of this would be if I'm moving left or right. And as I said, left or right, inside, adding and subtracting, the insides are opposite. So x minus 2, I'm really subtracting a positive 2. I move right 2. Whereas x plus 4, I'm subtracting a negative 4 to get this plus in the middle. So that is left 4. Or you could simply remember that the insides are the opposite of what you think they'd be. So you see a minus on the inside, you're really moving right. Seeing a minus on an addition on the inside, you're really moving left. So an example, let's say we moved left 4. In the exact same way of up and down movement, you take the whole graph. I suggest the vertex, shift it left 4, and the slope is the same. You basically have the graph, as long as you maintain the slope at whatever new vertex you've drawn. So let's put it all together. Let's say we have something like this. So to start off, I keep saying let's move the vertex first. So that means let's look at the up, down, and left, right movement before I do any slope changes. So plus 3 would be up 3. Minus 2, because it's on the inside, inside's opposites, this is right 2. And then 3, finally, that a value that we're multiplying, this is our slope. And we know that 3 is really 3 over 1, so that's rise 3, run 1. Or we could call this, if I just look at its slope, right 3 up, or up 3, right 2, my new vertex from 0, 0 is now at right 2, up 3, right there. And we know that vertex actually signifies what these transformations are. So 0, 0 became 2, 3. Those are the transformations, and notice how they match up. The vertex will always come from these transformation values. And then we look at its slope. Up 3 over 1, up 3 over 1. What's that going to look like? Up 3 over 1, up 3 over 1, up 3 over 1, up 3 over 1. And I would say, even if I wasn't understanding the transformation in its actual mathematically accurate phrase, vertical stretch or compression, this definitely looks skinnier. So what's happening? I'm taking the arms of the absolute value function vertically and then pulling them, dragging them up, stretching them up so that the arms look like they're like a person's yawning, like stretching your arms to the sky. We call this a vertical stretch. And a factor 3. a vertical stretch. How much am I stretching by? By a factor of 3. So I'll add in a couple other transformations just to sum it up. We can have a vertical compression as well. And what's that going to look like? We said if the a value multiplied out front is less than 1. So let's say I have something like y equals 1/3. Rather than up 3 over 1, now we are up 1 over 3. And then instead of going right 2, let's say we go left. How do I go left? I add a value. So maybe I want to go all the way to the left 5. And now I want to go down, let's say down 9. Let's get crazy. So we say, find the vertex first. So our vertex, based on these values, positive 5 on the inside, which is opposite. So it's really going left 5, minus 5. And if we're going minus 9, that's down 9. That's my vertex right there from our transformation. So left 5, down 9 would be right here. And then from there, I would use the slope, our vertical stretch or compression, which, because it's less than 1, 1/3, it's a vertical compression factor 1/3. Vertical compression of a factor 1/3, which is a fancy way of saying its slope is just up 1 over 3. So up 1 over 3, up 1 over 3. So let's say I take that function and I say, I don't want it to open up. I want it to be maybe the blueprint of a really flat roof. Then all I have to do is take 1/3, that vertical compression, and make it a vertical compression in the negative direction by making it negative 1/3. That's a negative 1/3. And the second it becomes negative, nothing else changes. I'm still at a vertex of negative 5, negative 9. I went left 5, down 9. The only difference is the vertical compression factor 1/3 is just going to be going down in the negative direction. So down 1 over 3, down 1 over 3. And then we have a vertical compression in the negative direction. That would give me, strictly speaking, it's still a vertical compression of factor 3. We've just added on one new transformation, which is that we have a reflection across the x-axis. And that is every transformation that is possible, especially possible on my test. Because like I said, you will not see any values being multiplied on the inside during this test. You will only see A, C, and D.